speaker of the day, I believe, yeah, is my roommate, Fabian Hebestreit, who will lecture about the homotopy type of algebraic cobordism category.
Thank you, Rumi. And yeah, first of all, thanks to the organizers for inviting me to the program and then to speak here, but it's been great fun and it's somehow been a great experience to have so many people to bug with inane questions. It's been wonderful. Okay, so what I want to talk about, yeah, it's joint work with these other 8 people, and somehow this means that there's many ways to approach the subject, but I want to focus on the particular story that originally was sort of the influence Wolfgang Steimle and I had. And the idea is to consider the following, so let R be a commutative ring and D an integer, to consider the following sort of yet another version of cobordism categories, which will be in quotes for now, and then the first 20 minutes will make it precise. This category is supposed to have objects, chain complexes over R, and together with what Ranicki called the symmetric structure, i.e. An equivalence to the dual chain complex shifted by d-1, that's somehow the usual indexing convention for cobordism categories. That somehow, if you do this, if you compose it with its own dual, gives the standard inclusion of X into the double dual, and a morphism is supposed to be a cobordism of such objects. So a morphism wants to be span like this, plus an equivalence of, let's call these maps I and J, from the cofiber of I to the cofiber of J, dual shifted by D. Okay, and that sort of encodes Lefschetz duality. So now if you take X to be the chains on a manifold and W to be the chains of a cobordism, you will precisely find this sort of structure. And the reason one might care about this type of object is sort of, I think threefold at this point. The simplest example is somehow this retains very fine information. Sending a manifold to its chain complex retains relatively fine information in this thing. It's much finer than say, the symmetric signature of Ranicki. The second reason, and this is why I came into this, was that in odd dimensions, the methods of Sir Galatius and Oscar Randall Williams break to compute the homotopy type of the diffeomorphism groups. And Nathan Perlmutter and I, sort of in previous work, showed that something like this may be used to correct this. And somehow, this is sort of the group that records the obstructions to doing whatever Søren and Oscar were doing. And so, but I will not speak on that. And the third part, this is sort of what I will explain mostly, is that this takes on a life of its own and sort of becomes relevant in algebra, or in higher algebra. And that's sort of what I want to expound mostly. And as George mentioned, such a category cannot possibly exist because somehow composition of morphism wants to be, if I have 2 cobordisms like this, it wants to be the push-out, and push-outs just aren't associative. So such a thing is only ever going to be an infinity category. And so if you want to get an infinity category out, might as well start with infinity categorical input. So that's what I'll do in the first bit. And apparently I'm not a millennial, I'm going to drop all mentions of higher, infinity, homotopy, everything. So category will just mean infinity category throughout the talk. Okay, and so the input we're going to use was figured out by Lurie when he gave a talk, a course at Harvard about L theory. And so the input that we're going to use for the cobordism category is what's called a Hermitian category. A Hermitian category is a pair CQ, so this is the Greek letter kappa. There's going to be many Q's, and I need as many fonts as I can come up with. Where C is a small stable category. And kappa is a functor from C into spectra that sends 0 to 0. And is quadratic in the Goodwillie sense. So it sends strongly 2 co-Cartesian cubes, strongly co-Cartesian 2 cubes to Cartesian cubes. The relevance of these will be apparent in a moment. And somehow the example to keep in mind, and this is basically the only example I will give, is that C is the category of perfect complexes over a commutative ring, i.e. chain complexes which are bounded and degree-wise finitely generated projective. And Q is either of the following two functors. It's the Hermitian, it's the symmetric Hermitian structure, which takes a chain complex and sends it to the Hom spectrum from X tensor X into R homotopy fixed points. So this is precisely what one should mean by a symmetric form on a chain complex. Symmetric form of degree, well, so the signs come up, maybe I should say that first. So there's a convention to be made. You can put an op here or you can not put an op here, and this will influence the direction of these arrows. And somehow in topology it's much more convenient to have the arrows go this way, because that's what happens in a cobordism. In algebra it will turn out that the other way is more convenient. So what do I have to say now? There's more authors in this bunch that do not like topology than there are authors who do not like algebra. Therefore the convention ended up being the algebraic one. So this is clearly a contravariant functor, and this is what a symmetric form wants to be. And you can do similarly the quadratic functor by taking all of this and taking homotopy orbits instead of fixed points. Okay. D is just still a number that just records the degree of duality. Yeah. Right. And so somehow the point that Lurie makes is that this is an incredibly convenient framework, because somehow what do I need here? I need to encode somehow the symmetricness of this, I need to encode the dual and so on, and this is all present in the quadratic functor. And somehow to extract it from it, we need the tiniest bit of Goodwillie calculus that says the following: to such a quadratic functor, there exist essentially unique functors B and L, such that B is symmetric and bilinear. Bilinear shall mean in each variable separately it preserves cofiber sequences, and L is linear, i.e. it preserves cofiber sequences. Such that Q of X can be written as a pullback of the homotopy fixed points of Bxx. So the functor being symmetric means you're supplied with an isomorphism between Bxy and Byx for everything. And so if I put in Xx, this is an automorphism of that object, turns it into a Z2 space. Take the homotopy fixed points. And you can map it to the linear part, and those have to agree over the Tate object. So this is my notation for the Tate construction. Okay, and such that this is Cartesian. Now in Goodwillie language, this would be called the nth cross effect for some number below 2. I think the first, and this would be the linear approximation of the quadratic functor. But okay, this is just what I'll use. And in the example, the bilinear part is independent of whether I have the symmetric or quadratic decoration, and it's just given by the Hom spectrum over R from X tensor Ry into R minus D. And the linear part depends in the symmetric case. Well, if I want the quadratic functor to be the bilinear functor homotopy fixed points, I want this map to be an equivalence, I'd better make this map an equivalence. So this is just Bxx Tate, and the linear, the linear part of the quadratic functor, Jesus Christ, is just 0, because somehow homotopy orbits, homotopy fixed points, and Tate already form a fiber sequence. So if I put this 0, I get the correct definition. So the bilinear part is very important. The linear part is sort of a perturbation, mostly. So, for example, it will not influence the non-degeneracy in a little while. Okay.
I can't read the last two. So there's L, phi, or kappa. What?
L kappa SD and L kappa QD. The quadratic Hermitian structure and the symmetric Hermitian structure put into degree D. And so to continue, we need a non-degeneracy condition on this type of category. So CQ is called Poincaré, in memory of the late Andrew Ranicki, who called these things Poincaré. If for all objects in the category, there exists another object such that this bilinear functor is representable. So B blank X is supposed to be naturally equivalent to the Hom functor with values in Y. Okay, this encodes the dual of an object. So if this is true, if you always have such an object, you can call it the dual of X, and all these objects assemble into a functor from C up to C. And the requirement that it's Poincaré has two parts. First, this functor has to exist, and second, the functor has to be in equivalence. Okay? This is why we restrict it to perfect objects over there. And so in the example, the duality, because it only depended on the bilinear part, is again independent of quadratic or symmetric, is just given by the Hom complex from X into R minus D. So somehow this is how you get the duality and everything back out of the quadratic functor. But it's, even if you only want to consider this simple example, well, that simple example, it's quite useful to have this general setup of Hermitian categories and Poincaré categories around. Right, so maybe I can fit this here. So the ultimate goal was to define what type of object this is, and that will be the following. It is a Hermitian form in CQ is another pair XQ of an object X in C and an element in the infinite loop space of QX. So again, what does that do in the example? Well, it's a chain complex and an element in loops infinity of the Hom spectrum. Now that's just a cycle in your original, in the chain complex up there. So what this precisely says in that example is it's a chain complex and a symmetric bilinear form on it, or a chain complex and a quadratic form on it. And if CQ is Poincaré, then we can somehow, we want to ask this to be a non-degenerate symmetric form. For that we have to assume that the category is non-degenerate. Then we call XQ Poincaré if, well, to a bilinear form you can usually attach a map from X to its dual, and the same goes here. If the image of Q in loops infinity QX, so by the lemma, this in particular gives us an element in B QXX, and I don't want to remember that it's a homotopy fixed point. But then by the representability, an element in BQXX, sorry, loops infinity here, is an element in the infinite loop space of the Hom spectrum. That's just the Hom space. So this gives us a map from X into the dual of X. Call this thing Q sharp. And the requirement is if Q sharp is an equivalence. Okay, so this is precisely what you somehow would call a non-degenerate bilinear form in usual algebra. And the typical example of such a thing is what I mentioned in the beginning. It's if you're given a manifold, I fit that there, yeah. So if M is a D manifold, closed and oriented, then, let me give this a name, then the pair, the cone chains on M together with the refinement of the following form, psi cap, the fundamental class. This is a typical element in, this is a typical Poincaré form in the perf of the integers. I will not bother going to the universal cover and the symmetric Hermitian structure. Okay, and this is how you produce interesting examples in there. And indeed we can make a, somehow, this entire construction gives rise to a functor Poinc that I've used up there that takes in a Poincaré category, i.e. a pair CQ as here, and spits out a space. And it sends a pair CQ to the groupoid, i.e. space, of Poincaré objects in CQ. Okay, and this functor is sort of the principal player of this entire story. And I've just given you the sort of standard example of it. Okay, maybe, yeah. This is somehow exactly what Ranicki's symmetric construction of a manifold is. It's precisely that object up there. Okay, so now I've told you what the objects of this category are. Right? The aim was I wanted to make this precise, and I've just told you an object in here was supposed to, I defined the objects in here to be Poincaré objects in C, Q. So now what about morphisms? So for that, it's quite useful to, especially for the later parts of the talk, to do this in a bit more generality. Namely, we will define a version of the Q construction on this. So let me denote by Q dot. I need a bit of terminology first. So now I want to denote by SDN this span or co-span category that already featured in George's talk. So it's going to be the category that looks like this, where this here has n arrows. Okay, it's the category of, I don't know whether these are spans or co-spans. So with the help of that, we can define a functor from Poincaré categories to simplicial Poincaré categories. That sort of lifts the usual Q construction. It's given by assigning to a category C copper the functor category, the simplicial object, which in degree n is the functor category from SDN into C with a certain quadratic functor. And as George explained, somehow diagrams of this shape are sort of, they contain n cobordisms. By just looking at this lower end here, we have n such spans that agree at the ends. So this is precisely a model for n composable cobordisms. And all this upper nonsense here should just be fluff that we carry around to make this a simplicial object. So what I will require is that each square in this diagram is a pullback. Okay, so we look at those diagrams in C where each of these squares is a pullback. That's somehow the usual Q construction in equivalence Q construction. Yep.
I might have expected that. So a feature of a cobordism is that the cobordism itself has Poincaré duality in a relative sense. So that those co-spans are like Lagrangian or something.
Yeah, that is precisely encoded by this condition here. Yeah, I forgot to. I just thought it's supposed to be an equivalence, and this will be, we will take Poincaré objects in that eventually. And that will be precisely that condition. Yeah. Right. So I've told you what this category is, and as we've just discussed, this functor is supposed to somehow encode that sort of duality over there. So let me just give the formula for now, and then we'll do the example to see that that actually happens. So I need to tell you what this functor is evaluated on a diagram. And what can I do? Well, I have a functor from SDN into C. I can follow it by the old quadratic functor. Now I have a diagram in spectra, and I take its limit. Okay. And so let's do the example n equal to 1. So what is an object in Q1? Well, it's supposed to be a diagram of this sort. And that's exactly a diagram like there, except the arrows have turned around, because we're doing cochains, not chains. What is a form on this diagram, i.e. an element in the infinite loop space of Q1? Well, it's supposed to be a limit of this. So it's a form in here that agree here. And it's precisely the sort of structure you get if you had a geometric cobordism and took its cochains. And then you can compute what its dual is. I claimed, well, I didn't show anything, but I claimed this is again a Poincaré category, so in particular this should have a dual. Now you compute a bit, and you find that the dual is given by the dual of x, the dual of y, And crucially, not the dual of W, I mean, D is contravariant after all, but the dual of the push-out of this diagram. Okay. So in particular, if we take a Poincaré object, then this diagram is supposed to be isomorphic to this diagram, which precisely says X is isomorphic to its dual, Y is isomorphic to its dual, well, two closed objects at the boundary, and W is isomorphic, well, it's slightly encoded differently. It's saying W is isomorphic to a shift of the relative objects to the boundary. So this simultaneously does two things. It takes care of this being an equivalence, and it takes care of the shift being slightly different from the shift here. Okay, that's all encoded in that one quadratic functor, which makes it quite convenient. So I claim...
Fabian?
Yep.
Am I supposed to have as an example, like, if I take C to be perfect complexes on a stack,
Yeah.
if the cotangent complex is Poincaré, am I supposed to think of shifted symplectic?
I have no idea. I could parse half the words you said. Let's talk about it after. But. So what I've told you is what a cobordism is. So with that, I now should be able to make this definition. So I will define the cobordism category of this pair. This is supposed to be a category. And category means a simplicial set with a horn lifting condition, a quasi-category. So I need to give you a simplicial set. And it's the simplicial set that sends n to the Poincaré objects in Qn of C cubed. Okay. And now because of this condition, so an object, I mean, if you plug in n equals 0 here, you get precisely your original category C cube back. I mean, this is just a point and nothing happens. A one simplex is precisely a cobordism, as I've said, and then a two simplex consists of a diagram like this, where I've required this to be a pullback. So it's literally two cospans and some fluff that's determined. So that somehow is supposed to tell you that this really is an infinity category. A two simplex is literally two one simplices and their composition. Okay. So this is the main definition of the object I'm going to care about. And this example over there, this sigma, this gives rise to a functor now from the usual oriented d-dimensional cobordism category into the cobordism category of perfect complexes over the integers and the symmetric structure. I mean, this factors through 15 other categories, but for simplicity, let me just state it like this. Okay. So this just literally assigns to a manifold its chain complex, and we've recorded that it has duality. So here's the theorems we can show about this. So let me see. C, D, H, H, M, N, N, S. I tried to learn this by heart, but failed. There's an author missing. L. Sorry, Markus. Yeah. A kingdom for a vowel. So the first thing is, this thing still has computable homotopy type, which means this map actually sort of, we can determine what type of invariance it records. So the homotopy type of this category is some, for now, undefined object. It's loops infinity of the Grothendieck-Witt spectrum of the Poincaré category. So I will define this in a moment. But with that definition, we can now, I mean, somehow this is, I mean, this doesn't tell you much. I mean, you will see that this is defined so that this is true. But the second theorem is that we can compute the homotopy type of this up to an extension. And that is new even for somehow the fiber sequence I'm going to write down. Let me just write it down first. So if I have a stable category, I can in particular consider its K theory. And that K theory, the duality of of the category C induces an involution on the K-theory. So this spectrum is supposed to denote just the K-theory of C with the action given by Q. And I can take its homotopy orbits. Those come with a map into this spectrum, and that comes with a further map to the L theory of CQ. And the statement is that this is a fiber sequence. Okay, those are the main theorems that I want to present today. And if I get to it. The point is this fiber sequence was conjectured for various versions of Grothendieck-Witt theory and is known when 2 is invertible, either in the category or outside. I mean, when I just invert 2 on all these spectra. But somehow the whole subtlety of Grothendieck-Witt theory lies in the 2 torsion. Therefore, somehow this is an improvement of that. And in particular, it implies things like, because L theory and K theory have localization sequences, so does Grothendieck-Witt theory, which is a result of Markus Schlichting's.
What's the dependence of your K on your choice of Q?
Some of the spectrum I wrote here does not depend, but it has a Z2 action, and that's given by the duality.
Great.
So that depends. Particularly, it only depends on the bilinear part of Q, because the duality only depends on the bilinear part. Okay. Yeah, so this somehow is of independent interest, and maybe as a corollary, though this I definitely won't have time to make precise, one can also form the real K-theory spectrum of this sort of object. And if C is one of the examples above, no more. CQ is D perf R with, okay. Write this bigger. Is D perf R, and Q is either the symmetric or the quadratic thing, then one gets the aperiodicity statement that was conjectured by Hesselholt and Madsen. Namely, that their KR spectrum is 4 sigma minus 4 periodic, where sigma is the sign suspension. So this is supposed to be the genuine Z2 equivariant spectrum, real K theory. Somehow it's a version of that which in this particular instance really has the periodicity they expected. And this implies Karoubi periodicity. And that was also previously known when 2 is invertible, but no version of it without inverting 2 was known, and we can produce one. Okay. That's sort of the results I wanted to state and the advertisement I wanted to give. And now the rest of my time I want to spend on the proof of this. I'll sort of try to explain how cobordism categories can tell you something about Grothendieck-Witt theory.
What is sigma in this statement?
The sign suspension. So maybe I should have written this as S for sigma minus 4 smash KR. And this is just it's a zero-dimensional sphere with weird action. Sorry?
There was a different sigma.
Oh, this is not the sigma. Oh shit, yeah. It's not that sigma from Andrew. No. These have nothing to do with one another. I did not realize.
So
yeah,
these
sorry.
examples, the K theory, which is involution, and the L theory are the ones that we already...
Yes. Yeah. Exactly. Okay. So how do cobordism categories have anything to do with Grothendieck-Witt theory? So most of the results we obtain are sort of by analogy with the usual situation for cobordism categories, and let me remind you of 2 particular things. The first is that you can take the geometric cobordism category of D manifold, let me just leave the oriented away, and view it as a subcategory of the cobordism category with boundary that Genauer considered, and then you can take the boundary of this. I don't quite remember whether this sequence already featured in George's talk, but certainly the categories did. Then this is clearly a fiber sequence of categories. Somehow, if you have a manifold with boundary, you take its boundary, and the fiber of that is the closed object. And by the theorems of Galatius-Madsen-Tillmann-Weiss and Genauer, this sequence of categories realizes to loops infinity minus 1 of the MTSOD spectrum, of the suspension spectrum of BSOD, and the MTSOD minus 1 spectrum. And this is a fiber sequence. And somehow the logic of this was that Galatius-Madsen-Tillmann-Weiss proved that this is an equivalent, similarly that this is one. And the fact that this is a fiber sequence of spectra is a simple calculation with Thom spectra. And then Genauer showed finally that these two things are equivalent. And the second theorem is of a similar flavor. Because this is a fiber sequence, you can, in spectra, you can adjoin this guy over and get a map into the suspension, and that allows you to form the following colimit. Yeah, the boundary the connecting maps here are precisely the boundary maps of that sequence, and the answer is MSO. Okay. And what I will do in the next 20 minutes or so is establish analogs of these properties for the cobordism category, the algebraic one here. In particular, that means we're entirely reversing the logic of this. We're saying we can verify that the cobordism category sequence up there is an equivalence, is a fiber sequence without knowing their homotopy types. And similarly, we will show that the second equivalence without assuming that we have understood the homotopy type of the cobordism.
So Fabian, are you thinking of that sigma as sort of like a A-hat genus or algebraic version of the A-hat genus?
It's more the signature. I mean, it will come. This comes with a forgetful map to L theory by this result here, and that precisely recovers the signature and the what's the other thing called the Afkavern variant.
In the real case, it will give you A-hat.
Sorry?
In the real case, it's A-hat, but
In the real case, it's a hat.
but in that corollary C that you have up there,
Here. That which
it's values in KO, right? Or algebraic version of KO, in some sense.
takes values in algebra.
On the right-hand side in the
Somehow, yeah. The fixed points of this are what you want. I mean, this is KR, and the fixed points are, but the fixed points of this spectrum will turn out to be precisely Grothendieck-Witt. So no, it records the signature. Okay. So in order to make sense of this, I need to tell you what that cobordism category with boundary is. And here for the first time, or for the next time, it will become quite convenient to work in this general setup. To do that, I can define the metabolic category of a Poincaré category to consist of all diagrams of the sort so all cobordisms where one corner is 0 inside the first Q construction. Full subcategory, restrict the quadratic functor. And I mean, this wants to be a Poincaré object and a null cobordism of that Poincaré object. Right? Well, this is what it's supposed to be. So the cobordism category with boundary of CQ I define to be, and now I hope I got this index shifting correct, that there is none. I define this to be the cobordism category of the metabolic category. Okay, this has as objects manifolds with boundary now. And then, so the first theorem the 9 of us prove is that if you realize the sequence of course I did not do this right, but I of course did not do this right here already. There's the objects in the d-dimensional cobordism category are supposed to be d-1 dimensional. I forgot to put the shift here. Okay, at the moment, I mean, this is just shifting and index conventions, but some of the rest of the talk is structured around that index convention. So the realization of this is a fiber sequence. And we have an analog of Genauer's theorem. So the realization of the cobordism category with boundary is loops infinity minus 1 of the K-theory spectrum. And this is very much related to what George told us about a day or two ago. Okay, that's supposed to be the analog of the first thing I wrote on the board in the geometric setting. Let me just briefly indicate the proof. So the proof of one, I mean both proofs have two steps. The proof of one is this functor delta that takes the boundary here. This is a bicartesian fibration. It's a Cartesian and co-Cartesian fibration. And then Wolfgang Steimle already showed how to get the Genauer sequence without using the identifications of the homotopy types by precisely analyzing the situation in the geometric case, showing that it's a bicartesian fibration and showing that such guys realize two fibrations. Okay, so I will not say anything about the second part. It's a sort of clever application of Quill and B. And when when Wolfgang explained this to the 5 of us or something at that point, Thomas immediately realized that it also re-implies Quill and B. So this is a clever or very adapted restatement of Quill and B. But let me explain part 1 to you because it's quite nice. So what does it even mean to have a bicartesian fibration? Let me do the co-Cartesian case. Co-Cartesian fibration means if I give you a map in the target category, don't give it a name, and a lift of its source into the source category, call that n, then I'm supposed, that goes there under delta, then I'm supposed to find an arrow that maps to this arrow that is universal among all arrows that map to this arrow. So the initial arrow lying over this. So that's what I'll do. So what's the situation we're given? And I'll do this in manifold land because that I find easier to imagine. So at the end we'll have to turn all arrows around. I'm given an arrow in the cobordism category. Well, that's a cobordism. And I'm given a lift of the source into the cobordism category with boundary, under the boundary map. So that means I'm given a null cobordism of the source. Now I have to produce a null cobordism of Y and a cobordism between these cobordisms that is universal. But I mean, everybody should immediately be able to see a null cobordism of Y. Then you glue these two things together. And then in order for this to be now I have to give you a cobordism between cobordisms, and in order for this to be a map in the metabolic thing, it needs to be empty up here all the way. But now I claim, somehow, what is a cobordism between cobordisms? That's the same as gluing all these cobordisms together and giving a null cobordism of that. But what is gluing all of these cobordisms together? It's n union W, union W, union n. So that's just the double of n union W. And doubles are always canonically null cobordant. So n union over x w across the interval. That is a null cobordism of that thing. So somehow that verifies the geometric claim that the boundary map is a co-Cartesian fibration. But now if I just take this interval away, because certainly if I apply chains to this, it doesn't matter, then I claim all the operations that are now on the board I can perform inside the language of these algebraic Poincaré categories. I can take push-outs and whatnot, and this will be the Cartesian lift. So this part is the co-Cartesian lift. And somehow, because the cobordism category is symmetric, it's also, the flipping x and y gives the Cartesian lift. So that's why it's a bicartesian fibration. And that's quite nice. And if you go through this proof a little more, you will find that we didn't really need all that much about these three categories. So what we really show is indeed the cobordism applied to any split Verdier sequence. So what is that? That is somehow the thing one looks at for localization and then realize. Becomes a fiber sequence. So a Verdier sequence is a sequence in cat P in Poincaré categories that's both a co-fiber sequence and a fiber sequence. And we say that those things, well, we need to regard X once as an element in the bigger category. So somehow we're using the fact that this has a split. Any split Verdier sequence becomes a fiber sequence. So that's a localization theorem for these homotopy types of the cobordism category. Okay. So the same proof applies. Like this diagram still makes sense in that generality. And then for the second part, again it has two ingredients. The first is a theorem due to Ranicki, which says that, and I find this bizarre to this day, it says that Poincaré objects with boundary are the same thing as just forms, i.e. Hermitian forms, in the original category shifted by one. He calls this the algebraic Tom construction. And as far as I understand, this has neither a geometric nor a classical algebraic analog. This is purely a statement sort of in the derived category of a ring, or in a stable infinity category. The functor itself is quite simple. I mean, an object in the metabolic category is a span like this, and we just send it to the fiber of W2x. And somehow you now have to check that this acquires a canonical form, and the dual of this object turns out to be W. And so the map back takes an object to the co-fiber of the map to its dual. Somehow that's the equivalence between this. And the second statement is, so now the cobordism category of with boundary is just the realization of the Q construction on forms. But because there's no degeneracy condition anymore, every form is canonically connectable to 0. So the forms are contractible datum. So the forgetful map that just forgets the form satisfies Quillen A. Yeah, this map has contractible fibers. So it's a homotopy equivalence on realization. And this thing, by, I don't know, some people by definition, I mean, this is the classical Q construction, so that gives rise to the K-theory spectrum. I mean, this doesn't depend anymore at all on the quadratic functor. Okay. So that's the part 1. I guess I have a board left. Let me use that. But in order to carry out the program for step 2 here, we needed that up there was a fiber sequence of spectra. And while these are all E-infinity spaces, I can just add Hermitian forms by direct sum. This is a fiber sequence in E-infinity spaces and not a co-fiber sequence in E-infinity spaces, i.e. this map is not surjective on pi naught in general. So in order to get a fiber sequence of spectra, I need to produce non-connective deloopings of this. And that's where Grothendieck-Witt theory comes in. So I will define the Grothendieck-Witt spectrum, and I guess in Lurie's terminology it's only a pre-spectrum. The following way, just like you would in algebraic K-theory. Replace this is the same theory as when you replace the groupoid core of a category by its Poincaré object. If you do that in your mind, you will get exactly the K-theory spectrum. So the first space is just the Poincaré objects in CQ. The second step is I can take the Q construction of CQ minus 1. Right? This is a simplicial category. I can take the Poincaré objects in that. That's a simplicial space. Realized. And I can take the Poincaré objects in the twofold Q construction of C comma Q shifted by 2 things. Okay. This is the spectrum. I mean, these are the spaces in the spectrum. And then to give you the bonding maps, notice immediately that this space here, I mean, I told you it's a simplicial space, and in fact, it's a complete Siegel space. That it's a Siegel space is again this phenomenon that we've only recorded somehow n composable one simplices and fluff around them. And that it's complete boils down to this fact George expounded, that a cobordism is invertible in this category if and only if it's a cylinder, if and only if both arrows are equivalences in the original category. So this is a complete Siegel space, and the cobordism category is precisely its associated quasi-category. Somehow, to pass from a Siegel space to a category means it's a bisimplicial set and you take 0 simplices in one direction. That's precisely, instead of looking at the Poincaré space, the cobordism category only had the Poincaré object, like forgetting one simplicial direction. So in particular, with that interpretation, to give a structure map from Poincaré objects into loops of the cobordism category. I mean, to produce a loop, I only have to give you an endomorphism. Right? An endomorphism in a category produces a loop in its classifying space. So the structure map is just given by taking a Poincaré object and sending it to the endomorphism of 0 that's given by the closed object. Rinse and repeat in every simplicial direction. Those are the bonding maps.
And didn't you just say in the definition of this abstract cobordism category, wasn't this based on
Sorry? The objects in the somehow, but there's a shift, right? The objects in the cobordism category are the Q minus 1 dimensional Poincaré object. That's precisely what I have here. And I mean, this is Poincaré objects 1 dimension higher. So this is a closed D manifold is a cobordism from the empty manifold in the D minus 1 cobordism category. That's precisely what happens here. No, this is the space of closed objects in this category. That's how the numbers at least are supposed to work out. I checked them multiple times, but that's no guarantee, because I mean, somehow we're translating back and forth between covariant and contravariant, and this precisely messes up whether you shift by 1 up or by 1 down. And I hope I got them all correct, but somehow no guarantees. Okay, but so, was that a further question? So, with that definition, I mean, you immediately see that the first space in that spectrum is just the cobordism category. So, the theorem is 1, Grothendieck-Witt of CQ is a positive omega spectrum. And now I've just erased the theorem I wanted to prove. This implies A. A was the fact that the homotopy type of the cobordism category is loops infinity minus 1 of this spectrum. So I hope that's clear how that goes. And the second thing is this functor, Grothendieck-Witt from Poincaré categories into spectra, satisfies localization, i.e. it sends Verdier sequences to fiber sequences. In particular, when we apply it to the example CQ met CQ, CQ minus 1, we get the following fiber sequence. Fiber sequence. Okay, which is now the perfect analog of point 1 up there. Okay, and in Grothendieck-Witt terminology, this sequence is called the algebraic Bott sequence. And as far as I'm aware, again, it's only known when 2 is invertible in either the category or outside. And somehow. But in our language, it works in the full generality. So that takes care of part 1 here. So let me erase it. But then the proof of that result, I can actually somehow, all I want to say about it, I can fit there, is just as in K-theory. Once you've proven that the first term in the K-theory spectrum actually sends Verdier sequences or exact sequences with properties to fiber sequences, somehow the fact that the Q construction gives a positive omega spectrum is largely formal. And similarly, that the Q construction as the connective K-theory spectrum has localization is rather formal. And those just work in this setup as well. So let me not say much about that. And then we have the analog of this second property. And that is that that's property 1 here. because we have this fiber sequence, I can now adjoin this guy over and map from this into its suspension. And the statement is the colimit over D, SD smash the Grothendieck-Witt theory of CQD. This is exactly the L theory of CQ. And 2, we obtain a commutative diagram of the following form. So that, I guess, is the exact analog of this statement. The L theory is given by the add space, just as MSO by Thom theorems is given by the add space of manifolds. So we can make the following diagram. We can just forget. I mean, every Poincaré object is in particular an object. So that gives me a map down to the K theory of C. But as I said, the K theory of C has that action on it. But Poincaré objects are fixed points for that action. They come with an isomorphism to their dual. So that map actually lands in the homotopy fixed point. And then as part of the thing up here, I get a map into the L theory of CQ. And the claim is that these agree when I map them to the Tate construction. And this diagram is Cartesian. Okay. And that somehow, that one has this Cartesian diagram is essentially, I mean, it's a bit more information than part B of the theorem I had on the board. Namely, the fiber here is well known to be the homotopy orbits again. So because it's Cartesian, the fiber here is also orbits. That gives theorem B. But furthermore, such a diagram always determines a genuine Z2 spectrum. The category of genuine Z2 spectra is nothing but the category of naive Z2 spectra and a map into the Tate object. So this diagram defines for us a KR spectrum in genuine Z2 spectra. Okay? For which the geometric fixed points are L theory and the fixed points are Grothendieck-Witt theory, which was another conjecture of Hasselholt-Madsen that should be true of the KR spectrum. And now is the moment where I can finally say this once we do not know, currently, that our definitions of these objects agree with the classical definitions of Grothendieck-Witt theory. We have a particular quadratic functor, for which in all examples where both are computed, they give the same answer. And the warning is that functor, that's the only reason I'm not speaking about it, is neither the symmetric nor the quadratic functor. It's something in between, honestly in between. And that functor has many weird properties. For example, its L theory is not 4 periodic. So that's also why Karoubi periodicity fails for it. And somehow, full stop. So let me make that disclaimer. I don't claim this is the K theory spectrum of Hasselholt-Madsen. I claim this is a version of their spectrum where all the properties they wanted hold.
But if you invert 2 is
yes, and if we invert 2 in either the category or outside, it is the same, absolutely. Yes. So this gives theorem B, and then there's a little something you can do to get C, but let me not mention that. And instead spend my last 5 minutes on trying to give a word of the proof here. I guess this can go. Let me. But somehow, if this genuine quadratic functor really gives Schlichting's Grothendieck-Witt theory, then this explains a lot of the trouble he's had. Because many of the things that I stated here, somehow if you translate them back into classical language, this is not one of the classical L theory spectra, but if you invert 2, it is. So he has all the statements after inverting 2, and they hold just with the replacement of this theory. Somehow that's the philosophy behind that. Okay, so let me say one word about the proof, and then I'll be done. So how do we do this? The first observation is both sides satisfy that if I take this boundary map that goes from f of CQ to the suspension of f of CQ1, then this map is an equivalence. Somehow for L theory, this is a fundamental property of L theory that I shall not say anything about. This is, we'll say something. This is the same as it vanishing on the metabolic category. The metabolic category is the category of null cobordisms. So this somehow precisely encodes that L theory is bordism invariant, which is somehow the fundamental property. And indeed, somehow we can show that Grothendieck-Witt is the universal additive functor under Poincaré, and this result shows that L theory is the universal bordism invariant functor under Poincaré. And for the left-hand side, this is sort of trivial, right? If I jack D up by 1, then I'm missing a suspension, so if I put that back in, it's true. So step 2 is I need to actually produce a map. So from here to here, but then if I take this boundary map into the L theory space, then we know this thing will be an equivalence. And so if I give a map from Grothendieck-Witt theory into L theory, it will automatically factor over this colimit. So how do we get the map from Grothendieck-Witt theory into L theory? Well, you actually need to look in the definition of both. And let's do this somehow on the first space of the spectrum and there on the 2 simplices, because this is what I can draw. So what does a 2 simplex in the first space here look like? It's an object like this. No, let's call this Z, W double prime. Okay, that's what a typical object looks like in the first Grothendieck-Witt space, and then in the 2 simplices. And somehow, what does a thing in the L theory space look like? Well, as I said, the L theory space is supposed to consist of adds. So what is a 2-add? A 2-add is supposed to have the combinatorics of a 2 simplex. So somehow this is given by replacing the Q construction by what we call the row dot construction, because I don't know what this is. There is a better letter. We're just this category SDN is replaced by the full face category of the full face poset of the simplex. So an object in here looks as follows. It's 3 closed objects, 3 cobordisms, and 1 null cobordism of the whole thing. Okay, and so we have to, out of an object like this, which is a pullback, we have to make an object like this. But that's quite easy, because this is 2 composable cobordisms, and this is sort of composable cobordisms up to cobordism. So what I can just do is I can put X here, Y here, Z here, W here, right? That's the cobordism from X to Y. W prime is a cobordism from Y to Z, and W double prime is a cobordism from X to Z. That is how I've made these things. And now you see that somehow, but in this thing they were equal, so I can put the cylinder over this composite here. But the cylinder is again just W double prime. Okay, so this records that somehow this is n composable 1 adds, and that's a special case of an n add where a lot of stuff is degenerate. So this is how you get the natural transformation. On higher simplices, I'm not going to draw it. And so for the third property, so now we have a map. By the first property, it suffices to check that this map is a homotopy equivalence on 1 homotopy group that's independent of the quadratic functor. And so we can choose that cleverly. Choose it to be pi minus 1. That this map is an equivalence. So what is pi minus 1? Well, on this side, I claim that both these maps are equivalences on pi minus 1. So let's start with this one. And then all the higher ones here as well, which gives that the map on the colimit is an equivalence on pi minus 1. Here we know what the co-fiber, what the fiber is. The fiber is K theory of C, connective K theory of C. So it has no pi minus 1, and it has no pi minus 2. Right? Done. That's why this map is an isomorphism on pi minus 1. And to check that this map is an isomorphism on pi minus 1, I need to check that it is an isomorphism of pi naught of the first spaces. But the first spaces I know explicitly. So to check this map, we check pi naught of the n goes to the Poincaré objects in Q dot CQ. That is the Grothendieck-Witt side. And on the other side, we check pi naught of the simplicial set n goes to the Poincaré objects in this row dot construction. But now comes a lucky accident. Pi naught of a simplicial set only depends on the 0 simplices and the 1 simplices. And if I only give you the 0 simplices, they're just a point in both of these cases. And if I give you the 1 simplices, then in this side, I only get this span here. And on this side, I get one boundary of the simplex, which is just one side. So these sets just agree on the 0 and 1 simplices. So this is an equality on 0 and 1 simplices. So certainly an isomorphism. So that shows 1. And then how many minutes do I have? -2, so let me not write anything anymore. For the other thing, it's now fairly easy. You take this map and you apply to it this boundary map. Then you get into the shift of it while shifting the quadratic functor as well. And somehow if you do that on both of these constructions, we know what the homotopy fiber at the top is. It's K-theory, right? The fiber of this map is always K-theory. And then it's a little exercise in equivariant homotopy theory that the same thing happens on the bottom. So that's somehow if I stabilize this by one step, I get a Cartesian square. But a Cartesian square in spectra is also co-Cartesian. And then as I iterate that construction and take the co-limit of the upper line, I get L theory. And it's another little lemma in equivariant homotopy theory that as I shift this spectrum around and take homotopy fixed points and the co-limit, I get the Tate construction. Co-limits of push-outs are push-outs. So this square is a push-out and we're in spectra, so it's a pull. Okay, das I get. So this is Cartesian. Thanks.
Question?
Have you done some computations at the prime tool to see whether it would potentially agree?
Markus has, I have not. And probably other people, like who knows? I have not even met all of these.
I meant one of them.
So, what, sorry?
By you, I meant one of them now.
Yeah, the answer is then yes, and I'm the wrong person to ask. Somehow I came to this from this, trying to understand this cobordism category and its homotopy type. Most of these, somehow in particular, Baptiste Calmès, Yonatan Harpaz, and Denis Nardin came to this looking for a universal property of Grothendieck-Witt theory. And they found that somehow the old machinery does not work on the two torsion. So somehow this was, to an extent, calculational. In the end, analyzing the homotopy orbit spectral sequence for this K-theory homotopy orbits thing can be hard. So, yeah.
Other questions?
How about over the sphere spectrum?
Yeah, so the L theory of the sphere spectrum is already somehow the theorem, like this type theorem is supposed to say that Grothendieck-Witt theory is not much harder than K theory up to a orbit spectral sequence because L theory is understandable. But L theory of the sphere is actually not understood. It then depends a little bit on what quadratic functor you put in.
The same one that you did for perf. R.
Yeah, that's actually more complicated rather than less complicated then. If you put in the genuine one, we understand pi naught of this. It's the Burnside ring. Somehow the universal L theory spectrum doesn't have pi naught z. It has pi naught z plus z, which is a bit scary. But yeah, computations on that are still difficult.
Questions? Thank you, speaker.